Now you can hear me, right? Oh, I can't hear you. You're muted.
I was muted. You are right.
Okay,
You?
perfect.
Okay.
Wonderful.
It is okay
Let's
to you
see.
to show the screen, or do you want us doing that, or?
No, I think it works. Let me see. I'm gonna share
Good.
videos. Okay, is this shared?
Yes. Mhm.
It's good.
That's good. Is there any video or
Yeah, there's some
computer
videos. Let's see with
footage?
sound.
Uh-huh.
I guess. Let me see. Where's the sound? Here's sound.
Do you think the world is a beautiful place?
Well, it's okay, yeah?
I think the
Very
world
good.
is a beautiful place filled
You hear
with
the
wonder
sound?
and possibilities.
Okay.
Okay, so
Quite stressful everything here. I had a I had already a keynote today in presence here in Frankfurt, and I was planning to give this keynote now in the business class, but they don't let me into the business class. I thought I can just buy a ticket to get in there, so I'm just having some seat here somewhere at the airport, and hope the connection will be fine for the webinar.
wow.
And then the
Okay,
train
nice.
was delayed, but that worked
Translation.
all fine.
Is that because there's snow or something similar?
No. There was just one. I mean, I had the other talk until 3 o'clock-ish, and then it took some time to get to the airport, and one train was just simply not coming for whatever reason. And they're only departure every 30 minutes, so that made me delay like almost an hour at the end. But still, I made it. So that at the airport, everything was quick and fast.
Anna, hello, I know you're here. Ah,
Okay, so who is sharing this? Is this Joanne or Mel, or who's doing that?
let's say Mel.
Uh,
I
Hi,
will just
Simon.
announce the advertisement about the register because we are registering, we are recording the session, and after that, Mel should talk. Well, should
Okay,
present
and
you.
the
And
session is 1 hour in total. So how long shall my talk be?
is 1 hour in total, but we can save some time for the questions after,
Okay.
during, or is up to you.
Okay.
In theory, I think this will have a question and answers module to write the questions, or we can allow them to talk if wished.
Okay.
Okay, I don't see Mel still.
I will probably change my seat in a minute, a little bit further to the right.
Okay,
A little bit
Nell.
more. But the sound is okay. So my sound is okay. No disturbing noise in the
Absolutely,
background.
yes.
Okay.
Very good sound, yes. And Mel is also here.
Hello.
Hello.
Hi, Mel.
Hi.
Where is the message?
So this will be my perspective for my presentation today. Not much going on here.
Which
What are your
airport
hairs?
is
Look
that?
at your hairs.
It's Frankfurt. I just had to fly in this morning for another talk in Frankfurt, and now this evening I'm flying after this webinar back to Hamburg.
Okay. And you're in the business lounge?
I was expecting to go there, but typically I have a frequent flyer ticket. But this time I booked like a cheap other company, which is not included in the Smiles and More program. But I've still thought I can just buy a ticket for the business lounge, because I did this in the past, but they do not allow it with this specific other ticket I had. So I'm just sitting somewhere, try to find a quiet place here.
Okay, I'm sure it'll be fine. Did you try your slides?
Mm-hmm. Yes.
Yes,
Do it
the
once
sound for
more.
the video also works okay.
Sound okay. All good?
Yeah, no sound. I don't hear any sound.
That's sound.
Okay,
Should,
there is no sound here. I can go somewhere else where
okay.
sound is.
Do you think the world is a beautiful place?
Okay, I hear it.
I think the world is a beautiful place, filled with wonder.
And the video is playing also fine? Or is it
Mhm.
Yeah,
laggy
yeah,
or should be
it's
fine?
good.
As long as the internet connection is fine at the airport, we should be ready to go.
Okay. Maybe your phone might be faster.
Maybe I have my phone, I charged it just for the emergency case, but
Yeah.
currently it looks pretty stable here.
Okay.
I have a cheap contract which just allows me to download like 12 gigabytes.
Oh,
And I'm
right.
already at 10 or 11. I booked another two just for the emergency, but you never know how much Zoom actually takes then.
Yeah.
You hear the sound from the airport?
No.
Ah, okay. So it looks like the new AirPods work quite well then.
Yes, yeah. I'm always surprised when people don't hear the sounds around me.
True. You also have the new one, the AirPod Pro 3, or which version do
Yeah,
you have?
I have the 3. Yeah.
Have you tried the hearing support with them?
Yes. Well, I did it. I did a test, and
Yeah.
it came up negative. I thought it would say I had bad hearing, but apparently I don't.
Ah, okay. That also said I have either no hearing loss or just slight hearing loss.
Yeah.
And then when I turned it on, I found it a bit disturbing that I could I could hear my own voice with a
All right.
slight delay. So I found this a little bit disturbing. But there's some settings you can play with around, but I haven't checked yet.
Okay. Last week, people didn't really show up until about 5 minutes past. There's people in my group who said they will be attending. There's a new one named Yorgos who's working on presence, and he's actually doing the experiment, comparing the holographic avatars with also yours and maybe
Ah,
Didimo.
cool.
Yeah.
Ah, okay, cool. He's new on the project, or?
Yes, he's new. He's not new in the lab, but he's new on the project. Yeah. His
Okay.
name Yorgos.
Yorgos. Okay.
Won't attempt to pronounce the second name.
Sounds like a lot like Gyrokopolos or something. Is it from
Yeah,
Greece
yeah,
or?
yeah. From Giannopoulos. Well, I don't remember. Here they come. It's Michael. It's strange because here I see on my screen the name Anna Zappa, who's in Barcelona in University of Barcelona working on presence, but I see the picture of Simon.
For me, it's not. I have the name of Simon and his picture, and for Anna, I don't have any profile picture at all.
Oh, okay.
Maybe it's time for another update for you for Zoom now.
Yeah.
Mel, shall I?
Let's just wait another minute or so,
Okay.
because I know there's more people who are attending.
Mm-hmm.
So my flight is leaving at 8 o'clock, so I have all the time in the world.
Okay. Did you ever do a talk from the plane itself?
Not yet. Did you? I'm not
No,
brave enough for this. No.
no. Also, I found on planes when you do join the Wi-Fi, it's not very good.
Actually, this evening there is the handball European Championship game, and Germany is playing, and I'm a big handball fan. I need to
Ah,
watch it during the flight. So I did
okay.
it all the last time. Streaming is really horrible, so it's more like you get an idea what the current status is, but you can't really follow the game.
Yeah. Let's start at 17:03. One more.
Mm-hmm.
Okay.
So, hello to all, and welcome to the second edition of the Present Gives Art product webinar series. Before I hand over to Professor Mel Slater, who will introduce our speaker of today's topic, a few quick housekeeping notes. Please be advised that this session is being recorded for dissemination purposes, but rest assured your personal data and camera feed will not be captured. The recording focuses exclusively on the speaker and its presentation. If you have questions, please submit them via the questions and answer module for the moderators to read aloud. However, if you use the raise hand feature and you are unmuted, be please aware that your voice and comments and questions will be included in the final recording as it. Thank you for joining us. Professor Slater, the floor is yours.
Hello again. So welcome to the second seminar in the webinars organized by the Presence Project. I'm very pleased to introduce Professor Frank Steinicke, who's a professor of human-computer interaction in the Department of Informatics at the University of Hamburg. Earlier, he was professor of computer science at the Department of Computer Science in the University of Würzburg and chair of the Immersive Media Group. He's has many well-cited and well-known papers. He's also won many prizes like Best Paper, Honorable Mention for Best Paper at ACM Chi, IEEE VGTC, VR Technical Achievement Award, and so on. I won't go through them all. You could have a browse at his website. In the Presence Project, essentially, he's like the technical leader or the inspiration of the project, and he's working mainly on avatars, which is our virtual humans, which is going to be talking about today. So over to you, Frank, and at the end there'll be a chance for you to ask questions. Of course, you can post them in the Q&A anytime. Frank.
Thank you very much, Mel. Thank you, Maria, for the nice introduction, also for giving me the opportunity to talk a little bit about our activities within the Presence project. Unfortunately, I have to give this talk from the airport, so I have a quite strange setup here. There might be some announcements in between. If the sound or whatever reason the video is lagging, please put this to the chat. I will have an eye on the chat in case there's something odd going on. So as Mel said, I'm the technical manager of the Presence project, and my responsibility is here to work on those parts of the project which have a technical background. So we have different technical pillars, as you might have seen already in the last presentation last week. And today I'm going to talk about one specific of these technical pillars, which is virtual humans. So the Presence project itself, just to briefly summarize again, is this European consortium in which we try to increase the presence in virtual worlds. And as Mel Slater has introduced, there are different illusions which come into play when you think about the sense of presence, so the belief that you're actually in this world. And he introduced the terms plausibility illusion, place illusion, and also embodiment illusion. So meaning that place illusion, you really have the illusion that you are in this virtual world. Plausibility illusion, that you have the illusion that the events which are displayed and occurring in the virtual world are actually physically occurring to you. And there's also the embodiment illusion, that you have the illusion that the virtual body displayed in the virtual environment is actually your own body. And there's also other aspects of presence, such as the feeling of social presence or co-presence, so that you really have the illusion being together with other avatars or other users or other agents, despite the fact that you know that they're not together with you in the same physical space. And our work on presence is essentially on improving those different kind of illusions, as we said, by three different technical pillars. One is holoportation, and you will learn about this in one of the remaining webinars, which is about transferring the current representation of the user by a volumetric representation to some other users in the virtual world. We also deal with haptics, so providing haptic feedback, so really the illusion of being able to touch and feel vibrations and also force feedback of virtual objects. This will also be discussed in one of the following webinars. And today we focus on the third technical pillar, which is entitled virtual humans. And here we use those virtual humans either as full body representations of real users or as an embodied humanoid representation of some sort of AI. And the goals within this technical pillar is to improve the fidelity of these humans by providing an easy to use and state-of-the-art pipeline to realistic or to quickly generate efficiently realistic 3D human models. And the other goals are that you have the possibility to interact with these agents in case these humanoid models represent an AI in a natural way, so that you can have multimodal communication via gestures, via speech, via facial expressions, etc. And also the behavior of these agents should be realistic in terms of plausible full body movements. And here we use physics-based rendering, which will not be the part of this talk, but maybe a later talk given by colleagues from ATEN. So when we talk about intelligent virtual humans within this project, we mean two branches in which we can use them. So we think about having a humanoid representation of some user, which can be used to represent the user in the virtual world. That means you're done on the head-mounted display, and then you have this embodied illusion because you see this humanoid representation as yourself. And you basically map all your tracked movements one-to-one to this virtual representation of yourself. And this will then introduce the embodiment illusion, so really the illusion that this virtual body is actually your own body. Today, I'm going to talk a little bit more about this right branch here, intelligent virtual agents. So here the idea is that we can use a virtual humanoid 3D model not to represent a real user, but to represent basically the computer. So having some artificial intelligence which controls these agents. Within this project, we were working on a pipeline which allows to generate avatars by simply a two-dimensional picture of yourself, and then you can customize more or less the avatar with facial hairs, different clothes, etc. And here's just a quick selections of some of these avatars, which are all made just by a 2D picture. And as we have seen in the left branch 2 slides ago, we can use now these as avatar representation of a real user. So here in the left, you can see my postdoc, Kelly, who is also working in the Presence project with an Oculus Pro display, which allows to track her facial expressions, her body movements, and map this one-to-one to this avatar that you can see here. And you can see the latency is quite low, and the mappings of facial expressions and also body movements appears quite realistically. What I'm going to talk today in particular is kind of bringing together and blending these two very interesting and currently really hyped technologies of artificial intelligence and extended reality. And this then ultimately ends in these intelligent virtual agents. But before we dive into depth with intelligent virtual agents, I would like to briefly introduce these two terms so that we have a better understanding how we want to blend them. So if we talk about extended reality technology, this goes back to some of the pioneering work back in the 60s, for example, by Ivan Sutherland. So in 1965, Ivan Sutherland wrote a wonderful essay entitled The Ultimate Display. And in his essay, he speculated what an optimal, ideal computer display would look like. And he concluded that the ultimate display would, of course, be a room within which the computer can control the existence of matter. But what would that mean? He gave some examples. So he said a chair displayed in such a room would be good enough to sit in. Handcuffs displayed in such a room would be confining. And a bullet displayed in such a room would be fatal. But he also wrote that with appropriate programming, such a display could literally be the wonderland into which Alice walked. And this notion of a virtual reality environment, so a virtual illustrated space, which gets indistinguishable from the real world, has been often used in science fiction, cinematography, or literature to question if our perceptions are real or not. And movies like The Matrix from the Wachowski siblings is a prominent example of this perceptual ambiguity. There is obviously different ways how you can combine real and virtual content. And Paul Milgram has introduced the so-called reality-virtuality continuum. On this continuum, you can think about having the real world at the very end. So this is like the world of atoms in which we can touch, smell, and taste everything in the real world as we know it today. And on the far end, on the other side of the spectrum, we have the completely virtual environment, which only consists of virtual objects, and everything would be computer simulated. And obviously, in between, you can do some mixture. So you can come from reality and superimpose this reality with a little bit of digital content, resulting, for example, in augmented reality. Or coming from the other side, having a purely virtual environment, and you include some real-world view, maybe showing a video of the real world, which will end up in augmented virtuality setups. The space in between these endpoints is entitled mixed reality, and including also the virtuality is entitled extended reality. And within the Presence project, we work in this realm of extended reality environments with a focus on virtual reality. Already 3 years after Ivan Sutherland wrote his wonderful essay, he was able to build the first prototype of such an ultimate display. And here's a video snippet from 1968, which shows one of his colleagues demonstrating this first prototype of a so-called head-mounted display. And what you see is one of his colleagues using this technology, which is based on a beam splitter technology. So think about glasses through which you can see the real world, and onto these glasses you can project information. And I'm just replaying this again. So on top, you can see this electromechanical setup coming out of the head of the user, which is a tracking device. So this allows to track where exactly the user is and where the user is looking at. And this information is then used to display 3D environments similar to how we know today. Obviously, you see that the graphics were really limited back at this time, but the general components of a virtual world were there. So you had tracking, stereoscopic rendering, there was head-dependent or view-dependent rendering as well, and also networked computing. Obviously, within the last 50 to 60 years, this technology has really improved, and nowadays your virtual worlds can be displayed basically on consumer devices. Here's one example from the Oculus Quest already a couple of years ago, which shows how you can basically now interact in highly realistic computer-generated environments just with a couple of €100 for displaying for such consumer head-mounted displays. So that's the current state of the art in extended reality, and now have a look at the current state of art and the evolvement of artificial intelligence. If we talk about artificial intelligence, there is one important aspect, which is in the term we talk about artificially reconstructed intelligence. So the first thing that we have to understand what we mean by intelligence. And in cognitive science, it's not really clear what we mean with intelligence and how to define intelligence. A lot of intelligent tests, for example, estimate or measure how good you are, for example, in mathematical tasks or in spatial tasks or maybe in linguistic tasks. But according to research, there is a lot of different areas in which you can measure and define somehow intelligence. Maybe your kinesthetic intelligence, how well you understand, for example, movements of your own body. Interpersonal or intrapersonal intelligence, how well you can basically understand your own thoughts or the thoughts of others. It might be musician or musical intelligence as well. So there are different ways how you can define intelligence. For the scope of this talk and also for the scope of AI, this is often somehow summarized as all cognitive abilities of users or humans. And if we talk now about artificial intelligence, it basically means that this will then be human intelligence simulated by a machine in an artificial way. And I think that's a very important point to make with the current discussion about artificial intelligence, which is these AI systems are not intelligent per se or by themselves. They only simulate some amount of intelligence. And already back in the 50s of the last century, pioneers such as Alan Turing have thought about how can we actually define if something is able to simulate human intelligence. And so he also wrote a wonderful paper, Computing Machinery Intelligence, in which he's kind of thought about how can we measure this. And he defined something which was later called the Turing test or the imitation game. And this is the simplified version of this imitation game. So in this simplified version, the idea is that you have a real human C who communicates, in this case, just via text, either with a real human B or with a computer program A. And if the computer program A is able to trick the user C in believing that A is actually the human, then A would have passed the Turing test. So the thing or the aspect is here, can a computer simulate human intelligence in terms of natural communication based on chat-based communication only? So far, this Turing test has not really been passed yet. There are some reports that for some amount of time, some LLMs and chatbots were able to trick users. And I mean, when you communicate with an LLM and a chatbot, you really get this notion that we get close to this moment in which really chatbots can trick us into making believe that it's a real human controlling this. But still, if you kind of spend some time with this chatbot, ask some tricky questions, some interesting questions, you will notice at some point, this is probably not a human. But we are really getting close. So having a quick look maybe about how AI has evolved, similar to how extended reality has evolved over the last couple of years. So in its beginning, back in the 50s, AI was pretty much based on very symbolic and deterministic, basically programming skills. So the way how you programmed in AI was basically in a very traditional way by explicitly telling the computer what to do. So that's more or less the way how I learned programming. So if the value X is higher than some other value, do something like this. Yeah, and then the computer can, of course, also simulate the capability, for example, to play chess, etc. Then later in the 80s, 90s, the area of machine learning became more apparent. Here, the idea is that you do not explicitly program what the computer is doing. You still give them the corresponding features that they should look for, but they should learn the feature values by themselves. So in this case, for example, spam detection was a big thing back in the 80s and 90s, and it was really hard to program deterministically if something is a spam or not. But you could identify spam, for example, maybe by images in the email, by certain terms which are used like credit card and you have to pay immediately, all these kind of things. But it was kind of unclear in which combinations they should occur until something is spam. And then users had to basically annotate an email and say, hey, this is spam, this is spam, this is spam. And then the system kind of learned the occurrence and it was looking for specific features defined by the user or the programmer. So the user said, look for images, look for the term credit card, look for you have to pay immediately. And if those happen too often and the machine was learning this by users basically annotating the data, it learned more or less what is the specific value for a given feature. Then in deep learning, also, we got rid of the specification of features by humans. So here the idea is, and this is illustrated with these cat images, you just give the computers a lot of data. So you give them maybe millions of data. In supervised learning, this data is annotated. So for example, you tell, this is a cat, this is a cat, this is a cat, this is no cat, this is no cat, this is a cat, and so on. And now the computer starts to learn in something called a deep neural network, which we'll see in a second, and it will identify certain features by itself. So it will first, on the first level, maybe just have all the pixels. On the next level, maybe pixels are somehow filtered together so that they represent maybe like silhouettes or contours and edges of the image, etc. And they can be combined later to more complex objects like a circle, like a cylinder, or other representations shown on a 2D image. And then the system, based on the data that you provide them by telling, hey, this is a cat, it will start to learn what are the features which define a cat. So which of these features in my deep neural network occur most often if the users say, this is a cat. And obviously, also, you can already see how these AI systems can be tricked. So if you think about, you train a system with millions of pictures of a cat, and you will just color the first pixel of all these images with a white dot in the top left of these images. Whenever you say this is a cat, the system will for sure very specifically learn if there's a white dot in the upper column, this is for sure a cat, because this is a feature it will just learn is made of cats. This also shows, again, even if the computer is pretty good in identifying if a cat is displayed on the image, it's just simulating this intelligence. It has no semantic understanding that this is really a cat. It just learned what kind of features occur most often if there is a cat. And then this is the area that we work now on, is generative AI. And generative AI basically makes use in most cases of deep learning, but not necessarily. And it kind of uses trained deep learning networks to also simulate and generate content. And we have a look in a second how this works. And the work here on intelligent virtual agents is mostly based on generative AI. So let's see how these generative AI systems works. As I just mentioned, you can train a model. In this case, we call it a discriminator. So this represents somehow a model, and you fed it with image data, for example. In this case, you want to train the model to detect if something shows a real face or not a real face. So similar to the cat pictures, you now put into this model a lot of pictures which are annotated, like this is a real face, or this is not a real face, this is a real face, etc. And now the system on the first level maybe has all the pixels, and then on the next level they are somehow filtered together. And the further you go down, at some point it might, as I said, represent contours, edges, and higher level representations of this image. And now, since the data is kind of supervised, the system will learn which of these nodes in this model are important and should receive higher weights when evaluating if this is a real image or not, or real face or not. And at some point, the system will be pretty good in identifying if something is showing a real face or if it's not, sometimes even better than humans. In order to generate now something, you actually make use of this discriminator network. You introduce a second one, which we call the generator network. And here you basically put in some random noise in the beginning. And this model then learns how to use this random noise, and it has different weights, how this noise is combined to generate a corresponding image. And in the beginning, maybe the generated face will just contain of some noise. And then you put this noise to the discriminator network, and it will obviously tell you, hey, this is not a real face. So this is then fed back to the generator by telling, hey, whatever you have done here, your weights, adjust your weights in such a way that the new generated face will be more likely a face. Yeah, and then you do this a million times, maybe during the training process. And at some point, this generator model will generate more realistic representation of faces. And eventually, at some point, will generate realistic faces from which the discriminator will basically say, that's a real face. Yeah? And this is more or less how you can generate, for example, deep fakes or representations of humans which are purely computer generated based on all the training data that you provided for the discriminator, all the data here, but which probably a human can't distinguish if this is an AI generated face or not. Another thing I would like to briefly introduce here is generative pre-transformer, because we extensively use them also in our intelligent virtual humans. So this is essentially implemented, for example, in ChatGPT. And the idea is here, again, you work with probabilistic models. That means, for example, if you prompt the system, for example, with this sentence, it again takes a look at all the training data, in this case, not images, but text, and takes a look, what is the highest probability for the next word? And for example, if you prompt the best thing about AI is its ability to, then you get a series of words with a, let's say, some probability that this might be the next word within this list, which fits best. Fits best means this word occurs quite often in my training data after the sentence, for example, or after the last couple of words. And then you can play a little bit with the temperature in these models so that it's not always picking the highest probability, but maybe the second highest, the third highest, maybe a little bit randomized, so that whatever is produced here basically is also occurs more or less really human-like, because it's not deterministic. It takes with some random guess some of the best picking words. If you just would implement it like this, to be honest, there will be very quickly, the sentence wouldn't make any sense. Yeah? You would have still high probability of a next word, but there is not really grammar which is followed. And here n-grams come into play. Here the concept is that you do not consider a single word, but you can consider n words, like 2 grams, 3 grams, and so on. So you can basically say, well, if, for example, these 3 words come, highest are chances that those 3 words are the next 3 words, for example. Yeah, and you look not only for a single word, which might be the next one, but for n words, depending on how deep you define your n-gram model here. And by doing this, surprisingly, you get very reasonable results representing basically human language. You know, you prompt something, you ask a question, and it will provide, let's say, a quite high probability answer. Okay, let's have a look how we can bring this together now for intelligent virtual humans. So obviously, now you can generate 3D models of humans in XR and include some AI representations here. Let's have a look first how this looks like. This is an older version, by the way, before we started the Presence project. It's based on IBM Watson, but we will have a look at the current architecture in a minute. Just have a look how this looks.
How are you doing today?
Not that good. I'm having a headache and cannot sleep well.
I'm sorry to hear that. Can you tell me more about your headache? Is it a throbbing sensation or a dull ache?
It's more like a dull ache, I would say.
That sounds like it could be a tension headache. Are you under a lot of stress lately?
Actually, there were some deadlines recently.
Okay, stopping the video here. So as I said, this was already a couple of years ago, and you see the latency. And nowadays we just use basically better models. And I would like to briefly introduce the architecture that we are using behind this. So as illustrated here on the left side, this is kind of the part in which we make use of the input-output devices. So here the idea is we take a microphone, so the user can talk to some sort of microphone, which is either inbuilt in the head-mounted display or which is some external microphone. And so the user is saying something, and we transcribe this by using, for example, Google and OpenAI toolkits. Yeah? So we transcribe what the user is saying into a microphone. This is then used for the system prompt. So we basically generate a system prompt in which we tell the agent, hey, the user is saying this to you. And we basically then use the LLM to decide what would be your answer if the user is saying this to you. But we do not just generate an answer, what GPT is basically doing, but we also ask the LLM, for example, what would be a corresponding facial expression? Which would you recommend if somebody says something like this to you, or if you saying something like that back to the user? And also, what would be a corresponding body movement if the user is saying something like this? For those facial expressions, as well as the body movement, in most instances, we have some predefined animations. Yeah? So we have animations of the user who can smile, who can nod, who can shake the head, who can look frustrated, who can look happy or sad. And the LLM basically then tells us, okay, if the user, for example, says, you look great today, then the LLM decides, hey, from this predefined set of animations, you should pick the one in which the user is smiling. And then we basically play this animation, and the user would smile if you say something like this. Also, the agent would answer appropriately given by the LLM. For example, saying, thank you, it's very nice of you. And also the body movements might be, for example, a happy dance. Yeah? Again, we just ask the LLM what would be the corresponding realistic behavior. And this is then fed to the 3D rigged avatar or humanoid model that we have. We use also lip sync to have realistic lip movements. And optionally, we can also introduce an image prompt. That means, for example, if the user says like, how do you like my appearance? We will generate a screenshot from the perspective of the agent, which we will also fed then in the vision language model. That means the AI also will have access at certain instances to a screenshot of the environment and can comment on this. We don't do this in a constant streaming, basically for limited tokens which are available. Yeah, otherwise it would be quite expensive to, for example, send images to the libraries all the time. This implementation is quite modular. So currently, in most instances, we use cloud-based services such as Claude or Gemini or GPT. But as I said, this is modular. So we can also use local models, and we played, for example, with DeepSeek or other local models to test also, let's say, more privacy enhancing implementations here. But for many of the instances, we really aim, let's say, for the state of the art. So let's say the best models which are there. And this is currently, unfortunately, often cloud-based solutions. One interesting thing about this implementation, by the way, is that this is typically not locally running, but we use a cloud-based system. And that means if the cloud-based AI system is getting better, also our AI agent is getting better. For example, ChatGPT or GPT introduced at some point Korean as a language. So at that point, our agent was just able to speak Korean. Yeah? And there was not a single line that we had to change. This is kind of a very interesting observation because in the past, all demos were always getting worse over time. Currently, with these cloud-based AI libraries, actually, they're getting better over time. So here's one example in which you can see how we use different text-to-speech libraries, different speech-to-text systems, and also different LLMs. And here's the result of a user currently interacting with a 3D humanoid representation.
Do you think the world is a beautiful place?
I think the world is a beautiful place, filled with wonder and possibilities.
But the world can be very complicated sometimes, right?
I think you're absolutely right. The world can be incredibly complicated at times. It's not always easy to navigate all the different situations and feelings we experience.
Okay, here's another example of the, let's say, body animations. You could see some of this video already in which there were slight movements. And here's an example in which we integrate physics-based animation. This was done by our colleagues from Atanim, and I think Joanne will talk also in the webinar series, maybe a little bit about this later.
Hello,
so this
how
is an
can I assist you
illustration
today?
of an agent using physics-based animations, again, according to what the user says and how the user interacts with this agent. So in this case, for example, if the user looks away, in this case, we implemented the agent that it should follow the user's view.
How are you doing today?
I'm doing great, thank you. How about you?
I'm also doing great. Could you please move away from me?
Sure, I'll give you some more space. Please
And
don't
really
push me like that.
Something I would like to highlight here is really that this is physics-based animation. So this is
That's
not a
not a very kind
predefined
way to
animation which is just played. It's basically
Please don't push
generated
me like
based
that
on
was
the
not
interaction
nice.
of the
Don't
user.
push me.
So there's now some very interesting things that we can do with these intelligent virtual agents, which you can use as a representation of a virtual human in the virtual environment. So, and I would just introduce like a couple of experiments that we conducted within the Presence project. So one thing we were interested in, what happened if you interact with intelligent virtual agent and you use some fembular representation. So in this case, one of our students generated with this pipeline a corresponding representation of herself. And we generated a similar representation, but which is not really familiar to users who know this person from real life. And then we did some experiments with members of either her family or colleagues or student co-workers who know her quite well, and those who do not know her. And we compared basically different perceptions of these agents. And here we were interested, for example, in trust. And this was measured by a questionnaire, the ITS questionnaire, and it shows that the trust that you give to an agent is significantly higher in cases in which you use a familiar representation. Yeah? So you have higher trust to an agent which looks like somebody that you know from real life. So some of these work that we did, and I will show you some more, also highlighted this vision of passing the Turing test, that this is not easy doable with an AI. And one of the reasons is that if you want to pass the Turing test, so allowing or an AI could be able or should be able to trick you in making you believe that it's a real human. You actually do not necessarily need to simulate only intelligent human behavior, but you also need to simulate unintelligent human behavior. Because we know from real worlds, humans are not intelligent all the time, but there's also quite a lot of unintelligent behavior. And if you would just behave intelligently, the users would quickly identify, this can't be a real user. So to give you one example, if you ask, for example, one of our AVAs, hey, what is the square root of, and you give a complex number or so, it could be just calculate the correct answer. But humans typically can't do this. So that means in order to pass the Turing test, it would mean that the AI should pretend somehow that it's not capable of calculating this answer, or it should tell you, hey, I can just do that if I'm allowed to use a calculating machine or something like this. And this makes also kind of interesting to pass this Turing test. So that means basically that these agents should be able to also communicate somehow uncertainty. So they should be able to mimic uncertainty in their answers. So here's one example how this could look like, for example. So again, we have an intelligent virtual agent, and this is work that we conducted 2 years ago. Susanne Schmidt, my former postdoc, was the main author on this. And she simulated now an agent who is capable of simulating uncertainty. And this is how it looks like.
Maybe sushi, but I'm not sure.
So you can see by the linguistic information like, I'm not sure, maybe. These are linguistic properties, but there were also non-verbal properties like facial expressions, the way how she looks with the eyes, and her other facial expressions. So this is how we did this. So basically, we trained a machine model to simulate this uncertainty. So first, we collected some verbal cues like terms like I think, maybe, I don't know. And we collected some non-verbal cues by face capture of actors with different, let's say, facial expressions of uncertainty. We did this as a Q transfer, or used this as a Q transfer for virtual agents, so that the virtual agents could basically mimic these facial expressions. And when we use mechanical Turk annotations and ask users to evaluate the amount of certainty in these responses. So we had some 6,000 training videos in which we had facial expressions and verbal expressions, and the user had to evaluate the certainty. And this was based on scores from 0 to 1. 1 means, it looks like that the agent was very certain about this answer, and 0 means they were not appearing to be certain at all. This was used for training the models, and then we tested basically videos to evaluate the model. And what you see here is the result. So in the perfect world, on the x-axis, you see the ground truth. So the actual, let's say, level of uncertainty that we produced. And on the x-axis, it's the confidence that users estimated what this model will look like. And in a perfect world, this will be like a diagonal line. So we can generate basically something with 0% certainty or 100% certainty, and the confidence would also identify this is 0% certainty and this is 100% certainty. One of the reasons why it does not look perfectly, but still we have this, let's say, trend line. So there is some way of encoding uncertainty. The way it's not perfect is based on also the training data. So typically when you need to annotate the data, you would rarely give a 0% certainty or 100% certainty. So you have the central bias, and this leads also to the fact that this perfect diagonal line is a little bit going more flat. But still, you see, you can significantly encode uncertainty into agents. And we think this might be interesting, for example, in natural human IVA, intelligent virtual agent communication, because it allows you to encode uncertainty in the answers of the AI. So if the AI, for example, you ask the AI something, it will always just have some probability for the correct answer. So if you ask, for example, what is this object? It has some probability that it is a cat, for example, or it's a real face. But currently, it's not really communicated in the interaction. And we think maybe this natural way of communicating uncertainty might be one way to encode this kind of information. So another thing is now, how can this uncertainty, or how is this perceived? And here we staged an experiment in which users had to communicate with an agent, and there was a short narrative which had to be done, but at the end, for example, they had to ask, hey, when did Peter leave the office? And now the agent either gave a very precise answer, like it was 12:17, or it gave an imprecise answer, like around noon. And at the same time, it was either looking at the laptop or it was not looking at the laptop. So the idea is it might have looked up when exactly Peter has left the office, or it will just give an answer straight away. What we found is that in both instances, either in the imprecise or the precise answer, users evaluated the response more useful if the agent was actually pretending to look at the laptop. Yeah, so it looks like that users were more trusting the answer if the agent was pretending to look at the laptop before giving the answer. The interesting interaction effect that we found is when we looked at perceived anthropomorphism. So how much did you have the illusion that this agent is actually a real human? And what we can see is if the agent gives an imprecise answer, it doesn't really matter if the agent is looking at the notebook or not. It has quite a high perceived anthropomorphism. So users think it looks pretty much like a real human. However, if the user gives or this agent gives a precise answer, but it has not looked up the actual number, this really drops significantly down. So it's kind of interesting because it kind of suggests already that if a humanoid representation gives a precise answer without actually looking it up, it does not look as human as if it would have looked up the answer or if it would just give an imprecise information. Another thing that we looked at is not only how do you react to these virtual agents in subjective questionnaires and maybe our behavior, so how close do we get to the agent if they approach us, but also is there other body reactions or physical reactions of your body if you look and come close to an agent. So together with our biology department, we did a study in which we asked participants in a bus stop scenario to approach a virtual agent. And we call this the make the agent smile task. So you had to go towards the agent and look at the agent until the agent smiles at you. And for some of these agents, the agent would have smiled, but they would also sneeze at you. Yeah, this is illustrated in this video. So you go towards the agent, and some of these agents, and we used an aerosol animation and also some sound to mimic that this is a contagious scenario in which the agent is ill and is sneezing at you. From the real world, and that's kind of interesting, this has been shown with videos and in the real world, if we have this situation, the immune system will react accordingly. And specifically, we will produce a globulin, which is called SIGA. So that's like an antibody reaction, which can be considered as the first line of defense. Yeah? So it makes sure that the bacteria will not come into your mouth, for example. And this is an increase of this globulin production of SIGA. And we measured this pre and post of the experiments. And what you can see already here is that before and after the experiment, so this is measured in the salvia, we can see a significant increase in the condition in which the agent is sneezing at you. Surprisingly, we could also find this increase in situation in which the agent was not sneezing. Yeah? You were just approaching an agent and the agent was just smiling at you. And still we could see a significant increase in this SIGA production, which is really surprising because this was not found in the real world and it was also not found with videos. So if you just see a picture or a video of a healthy user, which is not sneezing, your SIGA level would be the same. So it was very surprising to see this increase here. We took a specific look into the control group. So why we could find, let's say, this SIGA increase in the control group. And there was an interesting correlation. So it looks like that the sense of being there, so your sense of your place illusion was kind of a driver for the control group. It was not for the contagious group, but for the control group. So the higher your sense of presence, the higher was your delta in the SIGA production. So that means higher sense of presence lead to the fact that even if you see a healthy avatar or agent in this case, your SIGA production goes up. And we found similar for the involvement, which was also showing the higher the involvement for the control group, the higher the SIGA production. So those were pretty interesting results, which were contradictory to what we would have expected from real world situations. So one of the arguments why this could be happening is the situation that the agents displayed might evoke the illusion of the user that they're ill. Yeah, so even if they have not sneezed or snoozed, it might be that that users had the illusion there is something odd with this agent. And this is somehow known from humanoid representations in virtual reality as the uncanny valley effects. So the idea that if these agents appear to be somehow uncanny, not really like real humans, they fall in this uncanny valley. And one of the hypotheses of this is it might be that we don't like them because we have the illusion that they are somehow ill. Yeah, so we did a follow-up experiment in which we specifically developed, let's say, some uncanny avatars with, let's say, unnatural eye movements, unnatural smile compared to natural smile and realistic eye movements. And we also did a representation of these comic kind of representation of agents. And then we did not include the sneeze condition anymore. We just basically did a pre and post test to see if we can observe an increase of the SIGA for this agent. And now this is what we found is for only the uncanny agents, so those with unrealistic eye movements and unrealistic smile and also unrealistic body movements, we could see an increase of this antibody within the salvia production. So that means an uncanny looking agent evokes your immune system to react as if this agent would be ill. Yeah, and this is kind of very interesting from a virtual worlds perspective because it gives you a new way of measuring uncanniness of agents. Because if this agent appear uncanny to you, it looks like your body is actually reacting towards this agent. We couldn't find this for the realistic agents or for the cartoonish agent, which is a very, I would say, interesting result given the uncanny valley debate. So let's have a look how these agents and intelligent virtual agents might evolve in the future. So one of the interesting things about computer science is that it evolves exponentially since its very beginnings. So here in this area of the integrated circuits, we basically know from Moore's law that the number of transistors that we can place inexpensively on an integrated circuit approximately doubles every 18 months. So in simple words, it means my computer will be double as good every 1.5 years. And this law is more or less valid since Moore's law, but even before integrated circuits, we had exponential advancement in hardware technology in the transistor age, also in the vacuum tube relay technology, and even during electromechanical computing. And having this knowledge is really useful because it allows us to kind of extrapolate how technology might evolve in the future. So let's have a quick look at maybe 2 highlights of my talk. I talked about Alan Turing, Ivan Sutherland back in the 60s. And we could observe that then 50, 60 years later, we are now at this stage in which we have consumer head-mounted display with quite realistic rendering. And if we want to extrapolate how will this technology further evolve within the next 15 years, we can basically just use this formula provided by Moore's law, which says every 1.5 years, my computer will be double as good as the computer that I have now. That means after 3 years, it's going to be already 4 times better. After 4.5 years, it's going to be 8 times better, and so on. And I leave the math to you to calculate what will happen in 15 years. Well, there is an advancement of 2 exponent 10 to come to 15 years and approximately doubling performance every 1.5 years. And if you do the math, you will realize quickly that this means that computer systems will be 1,000 times better. So think about this. That means that the computer that I'm working on, or my head-mounted display I'm working on in 15 years from now, will be 1,000 times better than the display that I have today. And just think about the kind of problems that you can solve if your system is just 1,000 times better. Yeah, this is the transition going from kilo to megabyte, from mega to gigabyte. Yeah, but think about like CPU performance, GPU performance, network speed, and all these kind of things. And if you think about what kind of problems will just be solved because my computer system will be 1,000 times better, you will maybe have a look at the graphics Turing test. So the graphics Turing test is a variant of the Turing's test I introduced to you earlier, with a twist that the idea is here that we want to render something in real time which we can't distinguish from reality anymore. And if you think about movie blockbusters, for example, it's already there. Yeah, you can't really tell which parts of this movies is computer visual effects and which one is really video recorded. The twist here, the idea and vision is really do this in real time. Yeah. So in Hollywood blockbusters, you still often wait a couple of minutes or seconds until the rendering is done. This is really about real-time rendering. So think about a computer game in which you can't tell if this is a computer rendering or computer game, or if this is a real-time recording of something going on in the real world. And this will, according to colleagues McGuire and colleagues, already probably happen in 5 to 7 years. And just to give you a notion how this will look like. So when I finished high school in 1996, I played computer games, and one of the best games back then was Tomb Raider, and some of the best renderings you could get was this representation here of Lara Croft. Just thinking how this has evolved then over the years, already 1.5 decades later, so 1,000 times better, Lara Croft was already looking like this. And have in mind, this is exponential advancement. 3 years later, Lara Croft was already looking like this in-game. And again, this is already 10 years ago, and just should illustrate how this exponential evolvement also occurs in graphics representation and high fidelity representation. And here's just a representation of the same 3D model of Eloise that we worked on for the last 6 years, and how the representation of Eloise within the virtual environment has significantly and drastically improved over the years. And if you just think about how this will evolve in the next 5 to 7 years, it really gets clear that this will be a representation which is so realistic that you can't distinguish it from reality anymore. And also the form factors of head-mounted display will get smaller and more lightweight, and eventually end up in a contact lens. And all big players in the field like Apple, IBM, Meta, Google, they all have filled already their patents on smart glasses and smart contact lenses. And I'm pretty sure this is something that we can already observe, but it will be more dominant in the future. We will see an end of smartphones as the primary way of interacting with artificial intelligence, but more and more smart glasses. And by the way, I'm also wearing a smart glasses here with an AI agent, which I can ask to take pictures and give me some information on the headphones as well. And we already observe this decrease of the smartphone market for the first time in the last 20 years or so. Since the last 5 to 10 years, we can see this decrease, while at the same time we see an increase of smart glasses. They're still not ubiquitous, and it will take some more years, but you see literally every month or so a new smart glass going to be delivered. And I'm very much optimistic and convinced that smart glasses will probably be the primary way how I interact with AI in the future. So coming to the conclusion of my talk, I started with this Milgram continuum in which we had reality on one side and virtuality on the other side. And I would like to extend this continuum by also introducing human intelligence and artificial intelligence as endpoints of a continuum. And this already makes clear where the real magic happens, because reality as we know it maybe today and human intelligence only is just one point of the spectrum. In the same way, on the other end of the spectrum, the purely computer-generated and virtual environments, so the pure virtuality, combined with maybe everything decided by AI, is also just an endpoint of the spectrum. And the real magic obviously happens in between, in which you combine human intelligence with artificial intelligence, but also the real world with digital content by using mixed reality, extended reality devices. And I think this is actually the area in which we will see major advancements in the upcoming years by integrating and blending these technologies together and really developing helpful application tools and systems for users to improve education, communication, and also provide, let's say, more sustainable ways as humans in a technological world. So thank you very much for your attention, and I'm pretty much looking forward for the discussion and your questions. Thank you very much.
So thank you very much for that fantastic and very comprehensive talk, which raises a lot of very interesting questions. And I haven't seen at the moment any questions posted in the chat or the Q&A. So now is the time, if you have questions, to actually post them in. My question is about, well, actually there is one. Well, I'll ask mine first. What do you think are the ethical implications for this? Because already today, like you go on Instagram and you see some scientists making some statements and so on, and then you look below the Instagram and it says this was synthetically generated. we're getting to the point where it's becoming more and more difficult to distinguish between reality and artificially intelligent produced videos. And in virtual reality, it's going to be more powerful because what's there is, or a mixed reality, it's around you. Like there could be someone in my living room right now saying something to me, and it's really realistic and it's all completely fake. So have you thought about what we can do about the ethical consequences of this?
Absolutely. I fully second this. I mean, it's, to be honest, it's already a problem which is there for decades. Yes. So still today, or even decades ago, you were not able, if the images, for example, that you see on a magazine are actually a real human depicted or a real human maybe photoshopped afterwards, or maybe even something completely computer generated. But still, it was just a 2D image. And as you said, now we are really in the area in which we can generate videos realistically, or even dynamically real-time avatars, non-player characters which react somehow to us. So these problems, which are already there since decades, now really get really obvious. And as you mentioned, you can generate these very quickly nowadays. So that means basically you can pollute the internet basically with deep fakes, with AI systems which look like me or like you. You can easily generate this from a lot of YouTube videos which are available of us, and they can just talk nonsense. And these images, videos can just be and pollute sort of the internet. So I think at this stage, we really have to deeply think about if, for example, there must be regulations implemented which, for example, annotate everything which is AI generated or AI modified somehow. Of course, we can enforce this, let's say, by higher authorities. So that's probably something which has to go to the European Union, for example. And there we have something like the AI Act, the General Data Protection and Regulation. So there could also be something like this coming up soon. But again, it means that only those instances, organizations, and countries which oblige to these laws will basically then make sure that this somehow is fulfilled. And we notice already today that a lot of the AI organization and companies are based, for example, in China or in the US, which do not oblige to the GDPR regulations, for example. And I think this is a huge concern. But maybe also talking a little bit on the political basis with the current situation that we have as Europeans, let's say, on the world map, and then with the things going on in the Asian countries and also on the US side, it might make sense to think about that we really kind of have to make sure that we, as Europeans, have our own AI systems which follow these GDPR regulations, but therefore they really should have to be good, yeah, and better, or at least as good as the ones which are provided by the big organizations from the US or from China. But this would really mean a lot of, let's say, investment from the European countries in the infrastructure. It might also need some adaptation of the GDPR regulation so that we have corresponding data. But I think with the current political situation, now is the time in which we might have, let's say, the willingness to invest into being more independent of the systems by others. And then we can implement exactly what you mentioned, some regulations, and make sure that the ethical, moral implications of deepfakes and AI-generated content remains visible for the users of these systems. And I think it's very important.
Thanks very much. There is a question, which is, are you familiar with the platform Engage VR and their integration of AI agents as avatars to interact in virtual worlds? And what do you think about these integrations for business and education?
Yeah. I haven't worked with this specifically. I'm aware of a couple of platforms in which you have integrated avatars like Character AI, for example. Yeah. Also within the Presence project, we work on, let's say, applications in which we can integrate multiple agents into these setups. Again, I think it's important from a moral, ethical perspective that I should know if there is a real human behind this avatar or if it's purely computer generated and AI controlled. So I think this is like a very important step for all further communication, because as our research has also shown, you react pretty much in the same way to an agent as if you would react to a virtual real human or an avatar representing a real human. And then more or less the same rules should apply. Yeah. So this agent should not come too close to me. It should go away if I ask it, for example, to go away. And I should know at least that this is an agent somehow, so that I have a better understanding maybe if things don't work well. And then I can also react, let's say, with this clear knowledge that this is an agent differently to the agent than to the real user. So this is my, let's say, 2 cents on having virtual worlds in which you have multiple agents running around. You should make sure that users know which of these agents are real or not. And you can do this with a sign, with some representation. But I think we should really enforce this in all sorts of communication with agents, not necessarily in Engage VR only, in which you have the avatar representation, but also in character AI, in which you just have a chatbot with which you communicate. Or even if you call your flight agency to rebook a flight, you should also know if there's a chatbot communicating with you or a real human.
Yeah, I have this nightmare of in the future walking down the street with our augmented reality glasses and hundreds of virtual people come over to you trying to sell you stuff unless you've paid. I mean, I think this is a realistic vision.
Yeah, that sounds like a series of Black Mirror, but yeah, exactly those kind of things.
I think we have time just for one more. We started a bit late, so we can run over a couple of minutes. How far in time is an immersive game able to generate online 3D images of scenarios and intelligent avatars to play inside of and with, despite the device used?
Yeah. So, I mean, that's an interesting question, and you can answer them at different levels. So I think in a simple implementation, this would already be possible today. Yeah. So regarding the intelligent agent, again, you can provide some predefined avatars. Maybe you provide like 1,000 different avatars, and then I can tell in real time, hey, I would like to have a male 40-year-old professor looking like avatar, and then it just picks the predefined one. And you can do a similar thing, let's say, with 3D content. Yeah, you can have numerous assets, and then I'm telling, hey, give me a chair, and then it picks just one of the predefined content. Things get more interesting if you really think about everything is kind of generated on the scratch, yeah, without using any predefined models. Here, there's also some research work diving into this, but I say it's still kind of limited. It's really hard to predict how long it will take until you will just say, hey, give me a Harry Potter world, and then you just have a 3D representation which looks exactly like this, and you can walk around. But already with Gaussian splatting and nerve rendering, you can use some of the, let's say, 2D AI tools to do this. Yeah, so I would bet this is probably doable within the next 5 to 10 years.
On the Gaussian splatting, have you used it in your work? This is another question. And how would it change facial expressions and so on with virtual humans?
We have worked a little bit with Gaussian splatting, but a little bit more with nerve representation. So the idea using alternative representation within the virtual world, which is not based on polygons. We have not used Gaussian splats yet for representing virtual humans, but this is on our to-do list. And Kelly, so the postdoc I'm working on the Presence project, is right now working exactly on this, using Gaussian splats also to represent virtual users in the virtual environment.
Okay. And
sorry if I may interrupt. So if you're the person who was asking just disappeared from my list. So if you're interested in this, please get in contact with us, and then we can further exchange on this idea, because this is really something which is now very interesting for us.
And finally, do you think there would be a SIG, or do you know of any work of a SIG AI response to the uncanny nature of speaking to an avatar or to a virtual human that looks like someone they know? So yours was basically vision, but what do you think might happen with voice?
Yeah, interesting. So, I mean, you're right. Our focus was based on vision representation. So we had the eyes and body movements. We used always the same voice representation. I would bet, giving the theory of the uncanny valley. Yeah, so the uncanny valley was focused on visual representation. So it came from robotics. So it was based on vision and movement. But the theory behind this is, again, if something moves odd or looks odd, I, as a recipient, have the impression that there might be some illness associated to this representation. And I guess you could have something similar with the voice. Yeah. So if the voice sounds as if somebody is ill, so for example, I have a little bit of cough right now, I assume that even in the real world, if I talk to somebody and will do something like this, that this will already produce this increase of the globulin in the immune system. So I could imagine that you can simulate something like this in the virtual world if you really have this sick cues in the voice. I'm not sure what happens if you use like a robotic kind of voice, if this will also evoke the same impression. So that might be a very interesting thing to look at. We haven't really thought about this, but it's a very interesting aspect for future work.
Okay, so thanks very much again. It was a really, really interesting, fascinating, and also comprehensive talk, and illustrates the kind of work which is going on within the Presence Project, led by Frank, actually. So before we finish, I'll just say that next week, the 4th of February, continuing in the same theme, we have the physics of virtual humans, which will be chaired actually by Frank. And the talk will be by Joanne Jobera from Artinim in Switzerland. So thanks again for everyone who came, and thanks to Frank for the wonderful talk. Thanks, and bye everybody.
Thank you very much for your interesting question. Bye-bye from my side as well.
Bye-bye.
Thank you very much to all.